chat of this section. And this section, so the first talk is from Rui Rui from RISE, and he will talk about the topology in the election hole double layers. And please.
Okay, first of all, grateful to the organizer, especially Shoucheng and Keverson, for organizing this very nice workshop, provide an occasion for us to remember Shoucheng. Okay, so my talk will be a topology in electron hole double layer, and this is a topic actually initiated by Shoucheng and his students or postdoc. So when I heard Shoucheng pass away, it's devastating for me, and because I not only collaborated with him, we grew up in the same city of Shanghai, and actually went to the same university, Fudan University. So I know him for almost 30 years. So occasionally we do talk about physics and other things, but in collaboration, basically we start with a long time ago when I was doing experiment of fractional quantum Hall effect. So we have a lot of crossover when we have our individual passes. So this Chinese word says, 路茫茫其修远兮，勿将上下而求速. If I roughly translate this to say, I should take a long journey to seek internal truth. That's, to me, is the best describe of what is the journey of Shoucheng. Although he is say bye to us, but his spirit will always with us. And also for me, is very deep inside. We want to carry out what his ideal and what is, or even his goal to realize some of his physics insight. Okay, so I'm going to talk about what's the long time ago, during 90s, although we never wrote a paper together, but I'm deeply influenced by his ideas in physics. So first is at the time 90s, when I started the experiment 1990, already have those kind of intellectual resources there. For instance, Shoucheng and Keverson and the collaborators already work on the effective field theory about this. Of course, there are other many great theorists, especially Bob and Duncan as most influential theory. But meanwhile, we also look at those papers which relate to unquantized fractional states like even denominator. Okay, at the time was not get great attention because everything happens in those quantized states. Unquantized is like nothing happened, just temperature independent, and there's a resistive. And then first experiment by Zhang and Stormer Tree really point out this actually is a very strange behavior in terms of two-dimensional electron. Because this one half is supposed to have a highest density of states, but turns out this just like nothing. Nothing changed with magnetic field. And then, of course, come up a very transparent idea about the metallic phase of this result. And of course, at the same time, HRL and James picture come to emerge. And that leads to my experiment a couple years later to really measure the composite fermion properties, such as mass and G factor and also other properties. So at the same time, emerge is the global phase diagram in the quantum Hall effect, which has a large influence in the community in terms of metal into transition at a zero magnetic field, and all the way up to what happens for 1/2. Okay, so to this date, this still a very interesting, very debating subject. So the depth of this kind of early physical explanation in terms of field theory still influence today's thinking, even for experiment. Okay. So when I always chat with Shoucheng about his experience, because he has a very unusual experience. He is a theorist starting from gravity, then go to condensed matter, then he did a very deep field theory work, then work in IBM. So he told me IBM actually he benefit a lot from working in IBM because he knows, since then he knows semiconductor. And he was amazed by the property of semiconductor, which can be so pure and so cleanly described, and also the quantization of the Hall effect and such kind of thing really amazed him. So if we look at the semiconductor, we start with silicon and compound semiconductor gallium arsenide, and then later the thing I'm going to talk about, indium arsenide gallium antimony. These all have very nice feature about they provide the best material for industry, and in the end, each of them actually change our life. On the other hand, they also provide best material for condensed matter research, especially in low dimensional. So that's, for instance, integer quantum Hall effect and a fractional quantum Hall effect. And other thing, maybe this to be discovered, maybe also depends on those materials. Also, of course, now the material become much more vastly more rich and variety. For instance, graphene and other things. But if I look at the semiconductor alone, there is a corner of semiconductor which not been really utilized for condensed matter research. This is what we said, indium arsenide gallium antimony. So it turns out this light is brought out by Shoucheng's group. The chairman actually is the first author of this paper, really brings the light of how do we use these for fundamental research. That's the topic that I'm going to talk about. So it turns out during the 10 years afterwards, so we discover quantum spin Hall effect. We also discover exciton insulator in the same material, in the almost in a similar setting of this. So I'm going to talk about this in a very brief way. First is what is the material, then some quantum spin Hall effect, then largely how do we make a large gap quantum spin Hall effect. The idea is a room temperature, whether it is possible or not. That's what we also, I had from time to time chat with Shoucheng. He is always very confident, say this is in the future, but we can dream about this. Okay, this will be in the future, not right now, but we dream about this. So I'm going to talk about what's the progress maybe leading to this. So this material are called indium arsenide gallium antimony. This is inverted band and sitting in the barrier aluminum antimony. So since you have inverted band, you have this a pair of this edge state, which is a helical. Okay, so this velocity of this pair is very small. Therefore, this will be representing interactive one-dimensional edge state, which has by its own has very interesting properties. But for now, we are focusing on whether we can see quantized edge state in this sample. So again, also again, I should recall that not only Shoucheng provide direct ideal model for this. Also, we have from time to time many email exchanges. Especially this one is very encouraging for us. I read your beautiful paper over and over again and simply cannot withhold my excitement about this important breakthrough in the field. At the time, the data actually not perfect, but there's a very strong evidence shows there's an edge state, okay? But he already foresee that this can be improved, and we talk about many times over the conference, okay? So the material is like this. You have a so-called 6.1.8 family. So you have indium arsenide, which has an energy gap like this. Then you have gallium antimony energy gap. So the valence band bottom is higher than the conduction band top. Therefore, this is inverted. So once you understand this inverted, then theoretically, Shoucheng Liu and his collaborators work out this important proposal, really brings the light of this. This can be a topological material, okay? For me, I never heard about those things because I know this material for many years, but also I know there's a gap, but we never thought about this way. Okay, so this parameter says this inversion actually can be fine-tuned by gate, which is emphasized in this paper. So this is a very particular type of material that you can fine-tune in the parameter. So if you grow this MB, then you have such kind of structure. You basically have a gallium antimony, indium arsenide, then you have contact, and so that's the heart of the system. Your electron and a hole coupled to each other, and the coupling or the tunneling coupling hybridize these two materials. Therefore, you have a hybridization gap. So also you can have such phase diagram to turn the front gate, back gate, you get into this topological region in this area. Now, if you turn to this region, you end up a normal gap, simply the semiconductor. Okay, so what we are interested in a very small range of this parameter. This inverted, also very lightly inverted, very close to this critical point. So now if I look back, what is this this platform provide us? Is the first, if you look just a bare tunneling, then you have this quantum spin Hall effect, and you have edge state, and they provide a platform for other experiment with superconductor. Now, if you put a barrier in between, then you may be able to change the interaction versus the tunneling cooling interaction. Then you end up exciton, and in the ideal situation, you may have exciton insulator, and even you can have a superfluid if you can measure correctly. Okay, so that's the people who grow the sample. Okay. So the quantum spin Hall effect, actually first you want to do insulate a gap. So that shows that you can get a very insulating gap. The resistance is greater than 10 megohm, okay, in the Scorbino measurement. So in this very insulating state of the gap state, you can have pure data which is coming from the conductivity of the edge state. So this is a quantized if the sample is small enough. In this case, it's a 2 micron or less. Okay. Then of course you make small samples like this is a 3 micron by 1 micron, 1 micron, 1 micron. You also get a quantized conductance according to the Butic formula. And then by collaboration, which is promoted by Shoucheng with faculty, here is Kamola and her student, we'll be able to show that this edge state actually carries the current. So that's the current carried by the edge state if you turn into the peak or resistive region. Okay, so around this time, about 3 years after our first report, then theoretical proposal says since this electron hole pair existing in neighboring bilayers, that if you fine-tune in the system, you may able to get exciton formation or even exciton condensation. But to begin with, we have to get the exciton. Okay, and then later, of course, Alan McDonald's group and pay a lot of attention to work out the phase diagram for this particular system. And the phase diagram shows much more richer phases and phase transition behaviors in this system. But for now, we only focus on a very simple question, is whether there's a possibility that can find exciton, okay, spontaneous exciton. So the evidence for this is very recent in the same material, if have electron hole system. Now, if the electron hole are very dilute, so diluted that one electron basically only see one hole individually, then they can form a pair. Okay. Now, if too many electrons, too many holes, then there's no such kind of relation. Therefore, they have plasma. So the task is to find transition from plasma goes to exciton. Okay. So in terms of optics, the optics really is first we want to turn this density to very close to excitonic, but another is close is to semiconductor. Okay. Of course, in case of semiconductor, theory also predict there's an exciton formation, exciton condensation. But experimentally, that turns out to be more challenging. So we focus on this inverted, but a very dilute exciton condensation. So optically, what we can find is the following. If I jump out, if we calculate what dispersion of this condensate, and then this is the dispersion of condensate. That's the dispersion if we have one pair of exciton and you break the pair and let electron hole go far apart. That's the dispersion of this. And then if you measure the optical absorption, that's the maximum joint density of states. So you have an absorption line, and also you have absorption line here because these are almost flat. So you should have two absorption features. So indeed, we in the zero magnetic field observe this broad absorption related to this, and also more narrower absorption related to this one. Okay. Now, if you apply magnetic field 1 or 2 Tesla, this thing becomes really sharp. Okay. Also, the energy has a blue shift. Really means the exciton energy became slightly large under perpendicular magnetic field. So that's also consistent with the property of two-dimensional exciton. So further measurement is from transport, really measure the energy gap versus the density, and it shows a very dramatic change of the energy gap versus density, which is something like a critical behavior. So that's also fit into the description of the exciton, because exciton very sensitively depend on density. Other transport features are much less depends on the density in such a way. Okay, so the other thing is more recent is we try to figure out if you apply magnetic field, what happens for this edge state. But during this course, we find that in this energy gap under magnetic field, you can still observe oscillations in the gap. Okay, so that's a kind of a strange, because this is a metal, this is a electron metal, this whole metal. In between, you have insulator, but this insulator really shows some oscillation. And this has something related to recently highly debated observation of quantum oscillation in the insulator of heavy fermions. Right? Okay. So the feature of this is a frequency jump from metallics to gap region. What happens is if you plot this oscillation frequency in the gap, you find that this frequency is much higher than it would be if you extrapolate from the metallic region. So this is a metallic region, and in the gap almost go to 0. But here what you measure actually is much higher frequency. In our case, is about 2 times higher than it's supposed to be. So the explanation is that the Fermi surface under the influence of metal or carrier can have different shape. If the Fermi surface is outside in the metallic region, then you have this shape, which is by blue line. Okay, so the area became very small, corresponding to small density. But if you go to the energy gap, because the screening became very small, very poor, therefore the scattering became very dominant. So this will change the magnitude of the self-energy. Therefore, the Fermi surface expand at the time. So in that case, you have high frequency oscillation. So that's the theoretical modeling that shows this is in the metallic region. But by this point, once you get into the gap, this density actually has jumped like this. That fits our description, with our understanding about the screening property. Then the last thing is quantum spin Hall or quantum Hall topological phase transition, which was concerned by the theory for many years. So you have this conduction band, you have this whole band which goes downward, and this conduction band which goes upward in terms of the Landau levels. Then eventually they will cross at some point. And what happens for this point is the question. So theoretically, this will go into a regime which you have quantum Hall effect instead of quantum spin Hall effect. Okay, so this has not been observed experimentally. So we did this search, really look for the oscillation inside the gap. If you go to such a high field, so far we study the oscillation in the region, like several Tesla to 8 Tesla. But once you pass this to like 12 Tesla to 15 Tesla, you start to see another peak. And this peak we identify is coincide with this one. And after this will become a quantum Hall effect. Okay, so this will be a quantum spin Hall effect. And then you have phase transition going to quantum Hall effect. And this phase transition shows a peak, the metallic phase, because you have a 2 insulator in between there shows a metallic phase. And this metallic phase is very, very frustrating. So the noise, the signal is very noisy. Okay. So lastly, I just take 1 minute to show that we can make a larger gap topological insulator by playing with string engineering, just like the case for mercury telluride. Okay, so I'm skip all these details, just to use the different lattice constant mismatch, which brings type of spin, the string for the quantum well. So in particular, we want to compressive type of a string to change the band structure of the whole layer or the valence layer. Okay, and this actually has an overall effect to enhance the hybridization. Therefore, the energy gap were enhanced. Okay, so that's theoretically or even practically well known in the semiconductor industry, even for this particular material, for the application of infrared detector, because you want to change the energy gap by certain growth technique. But we borrow this technique, and we find actually we are able to achieve this. If you have a 0 strain, then 60K is a gap. And if you apply 40 you get you apply 2%, which means 40% of indium dope into this. You get 480K. So that's already above the room temperature. So that's also at the same time, NTT of Japan also provide a very similar result. Okay, so I will stop here. So the conclusion is the following. I think for this 10 years of journey with the initial suggestion proposal by Shoucheng's group, and also his constant care and discussion about this, we are able to push this from a theoretical type of curiosity research to all the way to towards the maybe a possible application. Thank you very much.
Question? Yeah.
About the exciton, I guess the temperature dependence of the gap you show is the gap for the single electrons, right?
Yes.
Is there any, I mean, like the collective gap, like the, I mean, if it's really a exciton condensation, then it's gapless. But I would guess there is some finite coupling, right?
Yeah. For the one we measured, actually, is in the region, not in both condensation, rather in the region called the BCS pairing. So that's a more less stringent requirement for the sample itself. So what we got is the following. Let me see. I can take this. This is the gap energy. Measure this. So the gap energy here is deduced by capacitance measurement, and then that's the energy gap just from capacitance.
That's the single particle gap, right?
Yeah, I think so. Yeah.
So there's no signature for the collective mode.
Collective mode is no direct evidence, but just from the spectrum, you're supposed to have a 2 line. We did a measure to get 2 lines. So that's maybe a little bit primitive, but still in the right direction. Yeah.
More question? Okay. Oh,
yeah. So this is very impressive developments. What do you look forward to next here?
Okay, I'm going to say like this. I have some slides, but I don't have time to do. Firstly, we want to grow aluminum directly on the edge of this. So that's what you already know, right? But we follow the recipe from Charlie's group, and we're almost done with this. But this is a different topic. And then second thing is Shoucheng has also a very bold proposal for room temperature. This is based on single layer tin, right? So that's so-called staining, and we also work on staining. We get some very interesting result. But the next thing is really try to grow this on the insulating substrate. Therefore, you can do transport. Yeah, but the energy gap we get actually is bigger than the theory predicted already. Yeah. Okay, thank you.
Okay, if no question, let's thank our speaker again.
Okay.
So our next